Hey guys, and we're back. Ooh, we cut that 15 minutes close. The system shuts off at 15 minutes, so we made it just in time. All right, but this is video number 3, so we're going to pick up where we left off, talking about the Arrhenius equation, okay? So here we have the rate constant is related to activation energy through this equation. So K is equal to the frequency factor, which I'm never going to ask you to calculate. It would have to be something provided to you, times the sort of inverse natural log of negative activation energy divided by RT. And we talked about how this is not the R that you memorized before. Take that R and then multiply by 101.3 to convert liter atmospheres to joules. And you get this new R, and that's the one we're going to use here because it's an energy, so we want an energy unit. Okay? All right. So now let's look at what happens when we manipulate this equation. Okay, so if we take the natural log of both sides of this equation, it's essentially integrating it. Okay, so if we look at sort of the integrated version of this equation and we graph and we put it in this line equation and we graph it, we see that the x-axis is inverse temperature and the y-axis is the natural log of the rate constant. And take a look at what the slope is. The slope is negative activation energy over R. Now, R is a constant, 8.314 joule per mole Kelvin. And if you knew the line equation for this, then you would know the slope, right? So slope would be equal to the negative activation energy divided by R. So if you know the line equation for a plot of inverse temperature versus the natural log of K, then you can get the activation energy from it. All you do is you take that slope, multiply by R, divide by -1. That's the activation energy. How do you know the units? Well, an activation energy is an energy per mole, okay? And the units of R are joule per mole Kelvin. I know that the Kelvin doesn't necessarily cancel out, but it kind of does inadvertently because the x-axis is inverse temperature. So that's where the sort of Kelvin goes away there. But then say your activation energy would be whatever units of R are left, which are joule per mole. But that's actually super duper small, which is why 99% of the time activation energies are reported as kilojoules per mole because that's a much larger, more rational number. Okay? Now, but this does not allow us to look at what happens to a rate constant when temperature changes, because we've talked about how K is dependent upon temperature. So the way in which we can look at the effect of temperature on K is we can actually just take this equation and look at two different versions of it. And you don't really have to follow the algebra here, but this is the exact same equation twice, and we're going to put them together. Okay, so we're going to algebraically manipulate them and bring them together. This equation is a big equation for us. And by big, I also mean you don't have to memorize it. Okay, I would never expect someone to memorize this. This is way too nasty. Okay, this would be provided to you. But what this equation allows me to do is it allows me to look at temperature versus temperature, the comparison of the two K values, and the activation energy all in one simple equation, which is just really, really, really nice for us to do. Now, there's a couple of examples coming up on the next slide. I'm going to work through these with you in the next video, okay? But we're going to keep going for now because I use my cell phone when I do the working out on a piece of paper, and I use screencast for everything else. So we're going to move forward. The next video will be me working out these two questions, okay? So don't worry. We're coming back to it. Video 4 will address this, okay? But moving on with video 3. All right, let's talk about the collision model. Let's talk about what it means to be a successful collision or an ineffective or an unsuccessful collision, okay? Because yes, rates are affected by concentration, and yes, rates are affected by temperature, but you also have to slam things together to have a reaction. So how good are you slamming them together, right? So what the collision model does is the collision model is based on the kinetic molecular theory, and it accounts for these effects and the effects of the size of the molecule. Okay? Because the central idea is that if you're going to have a chemical reaction, things have to collide. So their size and complexity will affect how easy it is for a collision to take place. Okay? Now, obviously, if you just have more collisions, you should have a greater rate, right? And if you increase the concentration, you should have a greater rate, right? Because more collisions equals higher rate. If you increase the temperature, things are moving faster, so more collisions equals greater rate. But let's look at just rates and collisions without changing concentration or changing temperature. What happens when you can't just sort of tweak something? Okay? Well, just because two things hit each other doesn't mean it's going to be a successful collision, because two factors have to be met. You could have one factor and you still don't have a successful collision. You have to have two factors to be successful. Factor number one, you have to have enough energy to break the bonds. If you don't hit it with that activation energy, that minimum energy required for a chemical reaction to take place, forget it. No reaction. Think Red Rover, right? When you played Red Rover as a kid, you didn't pick the hands being held between the two jocks. You picked the hands being held between the two nerds because you knew that it was a lower activation energy, right? But the only way you win at Red Rover is if you have enough energy to break their hands, right? That's what we're talking about here. But not just that, they have to be in the proper orientation for new bonds to form. Meaning, if you're trying, and I've got some pictures on the next slide, but if you slam something from the right side, but you're trying to perform a reaction on the left side, that's not going to work. They have to be oriented the correct way. And a picture is really the best way to show orientation. So I'm going to show that on the next slide, okay? When you meet both of these conditions, we say it's an effective collision. It will lead to a chemical reaction. If only one or none are met, we call that an ineffective collision, and nothing's going to happen. Now, let's be honest. Most of the collisions that take place are ineffective, okay? But that small portion that is effective, that's what's really driving the reaction. And when you increase concentration, when you increase the temperature, when you tweak these factors, you shift that distribution, what we were talking about before, you shift that Boltzmann distribution, and you increase the number of molecules that can be effective. Okay, so that's really what we're talking about here. All right, so let's look at our picture. So here we have two molecules, and we're trying to generate, 2 moles of NaCl, which if you read it by the colors, this would be OnCl, but they wrote it in alphabetical order, okay? But this will be OnCl, OnCl. And basically what we're trying to do is we're trying to form a bond in between the chlorines, and then we're going to end up with 2 NO molecules, okay? So let's look at an option or some options, okay? If this is the way the collision is taking place, I don't care how much energy you put into this, you are not making these products, right? You're going to end up making a diatomic oxygen and 2 NCl molecules. That's not what you're trying to make here. That's ineffective. Again, this does not give you the bond that you want to make. Ineffective collision. Only the final example, sorry about that. Only the final example is what you're trying to make. You're going to generate the bond here between the chlorines, making the diatomic Cl2, and you'll be left behind with the 2 NO molecules. Okay? All right. So that's going to be the end of video 3. So I will leave you now, and we're going to move on to video 4, which is going to be using my cell phone to work out those examples that we blasted past in this video. All right, see you in just a second.